Hi, so I have talked about this before in a previous video, but I thought I'd go to a bit more depth in this video, and actually that's these things. This is the Model Engineer and Amateur Electrician, and this particular volume is 1898. It ran from the late 1800s through to the early 1900s. Well, the bit I'm interested in, the actual publication, I think is still being published. The bit I'm interested in is that period of the 1890s to the 1910s. The reason I'm interested in that is because it has an awful lot of stuff in there that's really worth knowing. Now, there are two views of thought on this. One is the past contains secrets we've forgotten, and it's well worth investigating them and improving on those secrets. That's the thought I believe in. I believe that the past is absolutely jam-packed full of really good ideas that have been shelved or forgotten or weren't appropriate at the time and are stunningly appropriate now. So I really think you should be looking at what went before. Then there's the group of thought that what went before was a whole pile of rubbish, which is why we don't use it now, and we're all so much more advanced we don't need it anyway. And that's the group that I think are basically out of touch. I mean, if that's what you think, awesome, knock yourselves dead. I personally think it's a waste of time. But a lot of people think that, or rather, some people think that, and good luck to them, they'll never discover anything. I believe in the other side, and that's why I look at this stuff all of the time. And I have a whole section of these, 12 volumes actually, the first 12 volumes, jam-packed with stuff. And we took a example of this, the gravity battery, and made a video on the gravity battery, which was just stunning stuff. There's so much in here that I could do video after video after video on just the batteries contained in this. And this is a small section of what they talk about. They talk about all kinds of stuff. But I'm going to choose a number of them and go through the batteries. So it's likely to be quite a long video. But what I'll do is I'll title each section so that you can cover the battery section. And if you're particularly interested in that type of battery, jump to that section. Now, I'm going to do a whole host of them, right from a really simple one, which, to be honest, is pretty much the AA that we use today, which is hilarious when you think about it. It was a concern in the 1890s, and it's still being used today. It's pretty much the same thing. I'm going to do that, but I'm going to do some stuff that's forgotten, and I'm going to do it because I think it's worth preserving that knowledge and making that knowledge available, even if that knowledge is not strictly useful or really is a dead end. I think that's fine. I still think it's worth preserving it, and you just don't see this stuff anywhere. And then I'm going to do some stuff on batteries that are actually downright dangerous. And those dangerous ones fall under that preserve the knowledge. I don't think they'll ever really be used. I don't think they should be used, but I think they're fascinating in what they are, and that knowledge should be preserved despite the hazards and dangers contained in. So there's going to be quite a range. They're going to be titled so you can jump to the battery bit that you want, and I'm just going to go and get on with that. So this is called the Bennet battery, and it's named after the guy who came up with it. It was also called the tin pot battery because it was advertised to be made in Nestle tins. So you used those little condensed milk tins and made your battery in the tin. And obviously the steel or iron of the tin was what was used as one of the battery electrodes. So it's a really simple device. Now, the materials you used were iron and zinc, but the zinc had to be amalgamated, which means you wiped the surface with some mercury. The instructions were given on how to do that. You get a bit of zinc, swash it over with a little bit of sulfuric acid, get some mercury, rub it into the surface until it absorbs into the surface to amalgamate your plate, which I thought was awesome. But of course nobody is going to mess around with mercury these days. The mercury actually suppressed the hydrogen evolution reaction. If you just put pure zinc in there, you get quite a lot of hydrogen given off. The next best thing we're going to be able to come up with is a zinc case from a battery, which is exactly what this is. It's a zinc carbon lantern battery. There are 4 in there. I pulled one out, cleaned it, flattened it, and also got the carbon rod out of it. So the materials are really readily available to play with this, and that has been treated already. It's not actually pure zinc. It's a zinc alloy, and it very much depends on the manufacturer to what the alloy is. but they're alloying metals that reduce the hydrogen over potential of the zinc. So instead of amalgamating it, grab yourself a zinc can and use a zinc alloy, and that'll work really well. And the other side was iron. Now I'm going to use steel wool, which is pretty much the same thing with a bit of extra carbon in it, and I'm going to wrap that steel wool around the carbon rod that I've just got. You could wrap it around a steel nail if you wanted to, but I've got this carbon rod, so why not? Now we need relatively good contact between the steel and the carbon, so that won't do it. And we also need a separator because there's a chance of these things brushing against each other. So I've got a good old bit of J cloth here. Marvellous stuff. And I'm going to wrap that electrode in the J cloth, and it'll act like a kind of a separator, as well as tightening everything down into contact. Now what I'm going to do is put a bit of string around it, just to hold the whole thing together. And that will hold my iron nice and tightly against my carbon rod. I don't know why I'm wearing gloves at this stage, incidentally. All I'm doing is making work for myself. So let's take them off. There we go. Awesome. Now I can feel things. So wrap that nice and tightly around. Okay, there's my other electrode. Now the electrolyte for this is potassium hydroxide, and it's 225 grams of potassium hydroxide in half a litre of water. That's what's sitting here, and that's why I had gloves on, because that's a pretty concentrated solution if you think about it. So we put that in there, and then we're going to add our electrolyte. Now I'm going to attach it up to a couple of crocodile clips, and we're going to try and run that motor from our little Bennet battery. Back on with the gloves. Okay. And we'll just give that a little time to soak through. See if we can start that motor. Oh, let's see if you can see the motor. That's kind of impressive, actually. That's very cool. So that's the Bennet battery. Now, when you think about that Bennet battery, actually, it begins to remind you of other things. I mean, what we've got here is a bit of iron in a KOH solution with a metal contact. That metal contact, obviously, makes you think it would be independent of the kind of metal that was used. And if you think about the iron, if we used nickel with that, then we would have a nickel-iron battery. And if we used cadmium with it, then we'd have a nickel-cadmium battery. If we used carbon with it, then we'll have that original battery that was developed by that the Swedish guy, I think, that Edison is supposed to have stolen and replaced with nickel. So I'm going to try that with a bit of carbon against it, and we'll see what happens, because then we're taking that Bennet battery and we're developing it into the line of battery development right the way through to NiCads, which are current use today. So it's interesting, I think, to see how this early battery began and then developed later on into the more common types that we know. So this type of battery actually has disappeared. You won't see this anymore, but it has developed into other types. So let's grab a bit of carbon rod. And this time what I've got is a bit of carbon felt. And if I wrap that felt around my carbon rod, doing exactly the same thing that I did with the iron, but this time with the carbon rod, because it's the zinc that we're going to replace. Incidentally, all the time I'm talking, that Bennet battery is running away, which is very cool. Oh, I remember actually now. It was a pain in the neck to do this with gloves on. So let's roll up our carbon, put it in a bit of separator to hold everything together. And tie that up with a bit of string. Now, when we do this, what we'll effectively get actually is a hybrid supercapacitor, because we've got carbon on one side and metal on the other side that is being reacted with the KOH, and so we should be able to use this to make effectively a hybrid supercapacitor. But it is also along the transition line to nickel-cadmium batteries. Now, disconnect that. Obviously what we should do is change the electrolyte, because we have loaded that now with some zinc ions, so it's not strictly what we were hoping it would be, but we're going to run it anyway, just by replacing the zinc with our carbon electrode. There you go. That's actually kind of impressive if you think about it. So what I've got here actually is a bit of nickel. Now if you look at this closely at the surface of this, then that nickel's going faintly green, which makes you think that it is maybe forming a bit of nickel hydroxide on the surface. I plan on trying it. I'm not sure what kind of result I'll get. But we've gone from the Bennet battery, which is a zinc iron battery, to the Jurgen's battery, which is a carbon iron battery. Jurgen's used graphite, actually. And now we're going to try this little bit of nickel to make a nickel iron battery, so that you're seeing the progression of how that battery developed. These all operate around about 1.2 volts, incidentally. Okay, so a sudden thought occurred to me. The first one we did were primary batteries, and of course the nickel iron is a secondary battery. So I've pulled out this power supply and I'm just giving it a couple of seconds of charge, and we should be able to get that motor spinning just fine. It won't last very long because we haven't put that much charge on it, but it should spin. So you watch right there. And there we go. Okay, didn't last long, didn't put much charge on. But that's showing the progression from the Bennet battery right the way through to the nickel iron battery, and then obviously if we replace the iron with cadmium, we get a nickel cadmium battery. I thought that was absolutely interesting. Okay, so this is the Lalande battery. Now, the Lalande battery is what the Bennet battery originally was. So the Bennet battery, remember, was zinc and steel. And the Lalande battery is supposedly the same, but what they did with the steel is they covered it in a thick layer that was supposedly a depolarizer. This depolarizer was black copper oxide, which I've got here, and you make the paste using magnesium oxide, magnesium chloride, and black copper oxide, and you mix those in a ratio of 25 to 1 to 1. There's 25 grams of copper oxide there, 1 gram of magnesium oxide and 1 gram of magnesium chloride, and you mix that into a stiff paste. Then that stiff paste is spread onto an iron sheet and allowed to dry. Turned into a battery, matched against a zinc anode using the same electrolyte that we used in the Bennet battery, and you had the Lalande battery. Now the Lalande battery was supposedly a secondary battery, could be recharged. The zinc layer apparently became quite spongy, and in order to reuse it once you'd recharged it, you had to replace the zinc layer. Now that seems a little weird to me, but that's apparently what you did. So what we're going to do is mix up our Lalande paste, and we're going to smear it onto a bit of wire wool, give it some time to dry, wrap it around the carbon electrode. What I'm looking for is a stirrer. Wrap it around the carbon electrode and then see how it runs as a battery. So that's my copper oxide, magnesium chloride, vanadium oxide, and a little bit of water. Perhaps not quite that much water. And then give it a stir into a paste. Interestingly enough, the magnesium oxide and magnesium chloride act as a kind of geopolymer, and that really should be quite exciting to you. It is exciting to me, because if it acts as a geopolymer for the copper oxide, could it act as a geopolymer for other oxides as a way of making an oxide paste that would be self-curing? Certainly worth some investigation. Okay, that'll do. This is all a bit ad hoc because we're not trying to do a perfect experiment here. What we're doing is just demonstrating different battery chemistries that are in danger of being lost, so that maybe you'll go out and investigate them. So there's our little bit of steel wool. What we're going to do is pour that paste on, which actually is beginning to set already. And then we'll give that some time to dry. Okay, it's had time to dry. It's actually really hard. That little magnesium oxide, magnesium chloride trick seems very interesting. Let's try it on other batteries. Okay, so we're going to make this the same way that we actually made the Bennet cell, if you remember. We're just going to wind it around there. And this is a carbon rod that I've got here. Put a bit of separator around it, and then tie that separator around tight with a bit of string. So it's all a bit Heath Robinson, but all we want to do really is see if it works. Any optimization, if you like the chemistry, you fancy having a go at it, then go for it. The copper oxide, incidentally, is just a pottery glaze, so it's really easy to get hold of it from a pottery supply store, and it'll be really pure from there, in fact, because most of the stuff that is supplied through those are relatively pure. So a bit of string, just to hold everything together. I love it. Bit of dishcloth, bit of string. Seems to work a treat. Okay, let's pop that in a beaker. A bit of zinc on the other side. There we go. Gloves on because I'm about to put potassium hydroxide in it. And the potassium hydroxide is 225 grams of potassium hydroxide to 500 millilitres of water. So really quite a strong solution. Hence the gloves. And we'll give that a few minutes to soak in. Let's see if we get something. Oh wow. That's belting along actually. It's supposed to have about 1.2 volts. Well worth a look at. It's supposed to be a primary battery really. You can recharge it, but if you recharge it you have to replace the zinc. So there we go, an example of a lost battery as it happens. This Lalande battery with the copper oxide depolarizer on an iron plate is not something I've seen outside of those books that I showed you. I can tell that's going to run for ages. Okay, so I'm going to talk a little bit about the chromate cell. So called because it uses this stuff. This is potassium dichromate. There are various flavours of the chromate cell using potassium dichromate, sodium dichromate or chromic acid. And they were tremendously popular in the late 1800s, early 1900s. But of course the problem with these chromates is they're monstrous. They're really quite dangerous both acutely and chronically. And they were in fact one of the first chemicals on the REACH list. They reached their sunset date 2017. So after 2017 you have no possibility of buying that unless you have an authorization to do so and have made an application and have a genuine reason for buying and using potassium dichromate. If you don't, you won't be able to buy that stuff. It is just not available to anybody. But historically it was an important battery type, and I think that the information needed for bichromate batteries or dichromate batteries, same thing, is worth putting down and worth being out there so people know about it. You can still find some information on them, but actually it's getting more and more increasingly difficult to find reasonable information, particularly on how to construct them, because these were made by amateurs, just people who wanted to use them. Now you make chromic acid, as I say, by making this stuff into a bit of a paste and then adding a lot of sulfuric acid at 50% concentration. And that will make your battery. And the battery is a zinc anode and a carbon cathode. And it will react the minute you put the zinc in there. So the chromate battery was always with a submerged carbon cathode and then the chromic acid electrolyte. And then in order to activate it, there was some kind of lever mechanism that would slide the zinc down into the chromic acid to start the battery. And when you're done with it, you would pull that lever to pull the zinc back out again, otherwise it would just rot. So we're going to make our carbon cathode, in the same way that we've made lots of them. And that's just a bit of carbon felt wrapped around a graphite rod, a little bit of dishcloth, which is deer cloth actually, as a separator and a hold it all together kind of material, and then we'll tie that up with a bit of string. And that will make the cathode. The anode, obviously, we're using a bit of zinc, and here it is. It's a zinc dry cell that I removed the rod from and then flattened, because this was again another one of those where you were supposed to use amalgamated zinc. That is, you rub the surface of the zinc with some mercury. And if you're going to play with anything dangerous, then certainly mercury is top of the list. Mercury is a really quite horrendous material. You're just going to find very few people working with it these days, in the same way that you can't find people working with chromates. You get them in chrome conversion baths, incidentally, and of course chrome coatings, but they are excessive in their health and safety respect, and rightly so, to be honest, and in the disposal. This is not something you can just chuck down the sink when you've finished with it. You have to dispose of it properly. So there it is, there's our cathode, and we can put that in here. Again, we'll put a little motor onto that, and then I'm going to pour the electrolyte in. Now, the electrolyte that we're going to use is a dichromate electrolyte. So the potassium dichromate, all by itself, was made into batteries. But I'm going to use this secret sauce here. It's a late 19th century secret sauce. What it is 8.5 millilitres of 98% sulfuric acid. So this stuff here, which is another lethal thing to manage, 8.5 millilitres of that, 100 millilitres of water, and then 16 grams of potassium nitrate. So that's what's in there. That kind of forms a nitrate, highly active nitrate ion that attacks the chromate, and you get a little bit more of dissolution in there. It's actually quite a beautiful material. It's this lovely bright orange, so it is very attractive, but it is very dangerous. Now, not a lot dissolves of this stuff, so I'm just going to put in a bit, and I'm not really bothered about measuring it particularly. And all that I put in is probably 3 grams or so. Won't actually dissolve in this. So that's my chromate. All of this stuff has got to be disposed of properly. Electrolyte. And you can see that the salt is sitting at the bottom, and that salt will not dissolve. And we'll put that into there. And then when we slide that zinc into there, we should get a chromate, bichromate, dichromate, chromic acid, because there is some chromic acid formed in there, battery. See, that is one of the appeals of chromate batteries. They are very energy dense. I mean, if you hear that is just belting along, and will do so until all of that zinc is eaten away. The disadvantages of them is it uses this horrendous carcinogen. So it is such a shame that that material can't be used, because it is just so dangerous and poisonous. But the power out of that, I mean, you see how much we're putting in, tiny little bit. It is highly unlikely you'll be able to buy this material. Obviously I have a license and a reason for using this, but it's highly unlikely you'll be able to buy any as a residential address. But there you go, the chromate battery, how to make it, how to run it. Very, very easy, but really just for historical purposes. So the Daniel cell actually is an incredibly venerable battery. It's got a long history and actually is still used today. So if you think about the galvanic pile, which is basically just a disc of copper and zinc with a saltwater separator between them all stacked up, then that was one of the very first batteries. It morphed into the Daniel cell when it was separated into copper in copper sulfate and zinc in zinc sulfate, and those two electrolytes were kept separate. They were usually electrically bridged with a salt bridge, but you could use an earthenware pot where the electrolyte could go through the earthenware pot, and that was the Daniel cell, and clearly it was the child of the galvanic pile. Now, the Daniel cell is actually something that we use even today when you think about lemon batteries. If you take a strip of zinc and a strip of copper and stick it in a lemon, you've made a Daniel cell, same as if you do an apple or a potato. That's exactly what you do. All you really need to do is keep those two electrolytes separate. And you can do that with a separator or some physical barrier or just distance. And when we did it, we did a gravity battery where we used the specific gravity of the two materials to create boundary layers. And that kept things separate. And we morphed that into the halide gravity battery, where we used the same principle to keep the halogen and the electrolytes separate from each other by having those boundary layers relying on the difference in specific gravity, which is what a gravity battery does. So Daniel Cell's gravity batteries were extremely popular, and like today, everybody was looking for improvements. So this particular improvement actually came from about 1903, I think. And I think it's very applicable today. We could use the same ideas in the halide gravity cell. All I've actually got here is a little copper plate, so don't expect wonders from this battery. And it's been just hammered onto a wire where you can see that the bend in the wire is covered all the way with the insulator. That's just to make sure that I don't get a reaction going up the glass. I only want it to happen on that copper plate surface. And what you do is fill it with a bit of carbon. This is just an activated granulated carbon, and it's meant for pond filter. So that's what I'm using there. I'll give that a little bit of a press down. Now obviously if you're doing a halide battery you wouldn't do the next step, but as it's a Daniel cell variant, what I'm going to do now is add a layer of copper sulfate. Now if you're careful, you don't need to do the next bit, but this, unless I pre-soak this activated carbon, it will rise up. So I'm putting a layer of cotton onto there, and we press that cotton layer down, and then we can add our electrolyte. And the electrolyte is 1 mole of zinc sulfate. All that air is coming from the activated carbon. There we go. Now if I add my motor, here's my zinc strip. And there we go. And there is our gravity battery. Now the idea is that the copper sulfate is assisted to stay into its boundary layer by being adsorbed onto the active carbon surface. So that will keep this nice and clean and controllable as a boundary layer, and this as the copper sulfate layer. The cotton isn't strictly necessary, it's just that I didn't pre-soak it, so it will float until it gets to be pre-soaked. But I can see that you would use that in the halide battery as well, and that particular idea comes from 1903. So there you go, a lot of lost secrets about how to make batteries, what kind of batteries there are, and some ideas on construction and how to improve them. Now, I don't think that these ideas have been lost because they've been proved not to work. Sometimes it's just that it's a bit too dangerous, sometimes it's just they're forgotten, sometimes they just fall out of fashion. There's this whole wealth of information that people just, I think, should go back to. I mean, the Daniel cell, as we discussed, goes back to the voltaic pile, and I suspect even further it's probably what the Baghdad battery was. So there's this huge history behind these things, and remember, if we don't look at history, we're doomed to repeat it. So looking back, thinking about what was done, using that to develop further the batteries that you're making or that you want to develop will, I think, inform incredibly what it is that you are doing. And some of those battery systems that we've looked at from those this turn of the last century have been quite enlightening in lots and lots of ways. So I hope you enjoyed the video, and thank you very much for watching.